Hello everyone. Last session we talked about profiles and multiple sequence alignment, and today we will talk about the algorithms related to it. So there are various algorithms also for multiple sequence alignment. The dynamic programming one is also very frequently used for multiple sequence alignment. And also we have a gradual sequence alignment. And they are not just limited to these two methods. There are so many other algorithms. And I also talk about other types of them. The scientists are suggesting new ones every year. So this is typical that we have a variety for algorithms regarding multiple sequence alignment. You can also read them in the textbook about these two frequently used ones, but as I mentioned, there are new ones, and I also mentioned one of them, but I'm going to focus on the most frequently one, which is related to an algorithm about HMM. So you're already familiar with profile HMM. We talked about it in the previous session. So assume that we have multiple sequences, whether this is related to DNA or protein, doesn't matter, the procedure is the same. So what we try to do is to find the conserved region first, and we try to show them by match states. So when we talk about match states in HMM, we are talking about the conserved regions. And after that, in order to complete the profile HMM, we need to add insert states and delete states. They are somehow related to the mutations that I told you about, like we have deletion or insertion, and we can talk about these things in details when we see the example. And for match states, I already mentioned that this is related to the conserved region, but how do I decide about the conserved region? It can be considered as the highest relative frequency of an entity, either nucleotide or amino acid, in a specific position. So as you notice, each one of them, we can just consider them a position. For example, first, second, third, and so on. And in one of the examples I also showed you, it could be negative positions also for showing the location of a specific nucleotide. But anyway, in HMM, we are not talking about negative ones. Everything starts from the first position, and we continue as natural numbers. And the number of match states should be decided using a threshold. So that's how we decide that whether that position is a conserved region or not. We should define a threshold. For example, we can say if 80% of the position includes the same letter, like we have 4 T and 1 gap. So 80% now, as you can see, has the same nucleotide. So in that case, we can consider it a conserved region. If, for example, we had 3-1, then in that case, this was not a conserved region. And as you can see in this example, for this one, this is not a conserved region. Why is that? Because we have only 2A and 2T, maximum 40%. So it doesn't pass our threshold. So defining the threshold is important. In this picture, apparently they didn't consider the 80% threshold. The threshold was much less. But in order to make it sense, it should be more than 50%. And usually in the questions, we exactly tell you, consider the threshold to be, for example, 80%, 70%, or whatever percentage we mention. And it is not always the same as the number of positions in the multiple sequences as we mentioned. What about insert and delete states? Insert states in a profile HMM, about that, to consider insert entities, nucleotides, or amino acids in the non-conserved regions. And I will show you exactly what we mean by that, very similar to the mutations that we talked about. And for delete states, we can say to consider deleted entities in the conserved regions. And that's the reason deciding about the conserved regions and match states are very important. Otherwise, it won't be possible to design, insert, and delete states in a profile HMM. What do I mean by that? It means that first you should decide that these positions are conserved regions or not. If they are not, then based on that, we understand that whether a letter is inserted here or not. In biological format, of course, we are talking about nucleotides or amino acids. When I say letter, as computer scientists, we are just trying to design the algorithm. Okay, let's go through the example, and please pay attention to this one because it's very important. Of course, we will practice it in the weekly assignment, and I will try to deal even with this weekly assignment before the midterm exam, because profile HMM will be in your midterm exam as well. So please pay attention to this example, which is very important. Now, let's assume that we want to construct a profile HMM for these sequences. We can call them family of DNA sequences. It means that most probably they are homologous genes. Now, we have these sequences. Unfortunately, they're already specified about the gaps, because the sequence is actually like this: ACA-ATG. It just has 6 nucleotides. That's it. There's no gaps. But these gaps, we are considering them so that all the strings have the same size. Fortunately, it's given. Otherwise, it will be complicated in order to decide where should I apply gaps. Okay, so how do I understand that, for example, first position is the conserved region or not? So this is the first thing we should ask ourselves when we want to construct a profile HMM. So we should define a threshold. Assume that the threshold is 75%. It means that now that I have the highest relative frequency for nucleotide A, let's see for A, what's the percentage? It is 4/5 of the cases that I have A nucleotide. So 80%, which is more than 75%, I have A in the first position. So it means that this one you can consider as a conserved region. For the second one as well, we can say it for C. For third one, for A, 80% is more than 75%. It's okay. So this part, the 3 first positions are conserved regions. But what about the fourth position? For A, I have 20%. For C, I have 20%. None of them are more than 75%. So this is not a conserved region. The fifth one, you see the number of gaps are 80%, but when we are trying to find the conserved region, it doesn't make sense to say, okay, this is a conserved region, all of them are gaps. So it should be a letter. That's why this is not a conserved region either. This is the same, but for the last 3 ones, A, 100% of times it is A. So this is a conserved region. 80% are T, then conserved region. For the last position, 80% are C, so this is a conserved region as well. So in the middle, as you can see, this part is not a conserved region. So the designing is actually arbitrary, as we mentioned here, but we are giving some rules so that by obeying them, it will be pretty much the same. Because if we don't obey them, then maybe you are not designing a correct profile HMM. That's why there should be some limitations And based on that, we can design a perfect profile HMM. And by the way, there's a hint here. It has a gap in the conserved region. Why this is important? Now, in order to understand about the delete and insert parts, I should be careful about it. Now, when we talk about delete places, it means that we are talking about the gaps in the conserved regions. So I already know from the first to third and in the last three positions, I have conserved regions, right? But here I can observe a gap. And as soon as you observe a gap in the conserved region, then this part is a delete state. So that's how I understand about a delete state. And what about the inserted ones? It's related to this region, which is not the conserved region. Okay, so that's why I told you it's very important to first assume that where's the part that is related to conserved region. As soon as you decide about the conserved region based on the threshold, then you understand which part could be considered also as delete state and which part insert state. So in order to design it, this is the HMM related to that, but let's go through it in details in order to see how we can design it. So always we started with these two states. So start and end. These places are always there. And whenever the probability is exactly 1 on the arrow, you don't need to write the probability. If you don't write it, it means that for 100% of the cases, it will be this case. So first we started and directly we go to the conserved places or match states. So as you can see, these states, which we call match states, there are 6 of them. But why is that? The strings that we had here, all of them are 9. They have 9 positions, including the gaps, of course. So how come is that? Because we decided that we have these regions as conserved regions, and this region is not a conserved region. So 6 nucleotides. That's why I decided that I have 6 places for my match states. Okay, so from the start to P1. So I want to start it from the position 0, which is imaginary. Now we want to go to the first position. And this is a conserved region, the first match state. With no problem, we directly go to the match state. But what do I mean by that? It means that we don't have any other option. Directly we go to the nucleotide which belongs to a conserved region. But assume that from the first position I want to move on to the second position. In 4 cases, with no problem, we go to the conserved region. But inside our conserved region, we have a gap. That's why we need a delete state to show this one. So 80% of cases, I go to the match state. But in 20% of cases, I go to the delete state. You see? And as you can see here, I have a probability distribution. That was the reason last session I talked about probability distribution. What does it mean? It means that each one of them is a probability, and the summation of them should be equal to 1. So 80% plus 20% is equal to 1. Okay, now we reached the second position. From the second position, I want to move on to the third position. So let's take a look at the profile. Again, we have a conserved region, right? And all of them consist of letters. So with no problem, without considering any delete states, we can move on to the next one. And for you, in order to make it easy, that, for example, you say, I want to consider 1 here. because with no problem from P2, I go to the P3. Whenever you see the deleted states, in that scenario, it's very easy to construct it because the values that you use here are exactly the same as the previous one. Or in another word, the input transitions are exactly the same as the output one. So it's very easy to construct the probability based on them anyway. So these probabilities are exactly the same, so we don't even need to think about it that much, and we make sure that this is the probability distribution. So we are already in the third position here. We want to move on to the fourth one. So from the third position to the fourth one, we are getting out of the conserved region. But the thing is that ACA-ATC, this one from the beginning didn't have any gaps. We are the ones who applied the gaps, and this is artificial because the sequence actually had 6 number of nucleotides inside it. So it's like from the third position, we are jumping to the 7th one with no problem. From here also, we go to here, right? And again, from this part, we could say the same. So in 60% of cases, with no problem from the third position, we jump to the next conserved region, which happens to be in the 7th position. You see, 60% of cases, we go directly from P3 to P4. So P doesn't stand for position, it stands for place, okay, place or states. You can also show it with S1, S2, and S3, or M1, M2, whatever you prefer. But we should be careful. These are the conserved places, conserved regions, not the positions, okay? So this one is actually 7th position here for P4, but for I1 that I will show you, this is the 5th and 6th position as well. So in 60% of cases, directly, I go from the 3rd position to the 7th position to my next conserved region with no problem. But in 40% of cases, you see, AC, instead of having gaps and directly go to the next regions, I go to a inserted letter. So whenever you have such insert states, I can construct such a state, and I call it insert state. So D1 because I had only one delete state, and I1 because I had only one insert state. If you have more, then you can name them, for example, I2, I3, and so on. So I think this is clear that 40% goes to insert states, 60% directly goes to the next conserved region. Okay, now about this part. This part is also a little tricky to understand it. Now we are in the 4th position for these two. Now I want to see what happens when I move on to the next conserved region. From A to C, for one case, again, I reach another insert state. Whenever it happens, we don't need to define a new insert state. We define a self loop like this. It means that this one goes to itself, okay? And as you saw here, it happens. From one inserted nucleotide, we went to another inserted nucleotide, and we call it a self-inserted state loop. And again, from C to T, this repeated again. So whenever you want to consider the probability to calculate it, we should consider only for this region. Because for the conserved regions here, for 60% of cases, we already know that with no problem, we moved on from the 3rd position to 7th one. So in the HMM model, you can see that 60%, we already dealt with that here. But for this one, that for 40% of cases, again, I will have the probability distribution only for this region. That what will happen if we are here and we want to move on to the conserved region. Okay, so here I understood in 2 cases, I see, for example, from A to C, and again from C to T. For 2 cases, I will have inserted states again. And as I said, we don't need to define a new inserted state, and we consider a self loop. But what about the other possibilities? Now you see from T, I move on to the next conserved region with no problem. So for 2 cases, we have such a case. Now for 1 case, for string number 2, with no problem, I move on from T to the conserved region. But what about this part? Because for string number 3, again, I should do the same. For C, I move on to the gap. It means that directly from C, I go to A. So we don't count this one as C go to a deleted region. No, this is not a conserved region. If this one was a conserved region, I would consider it as a delete state. But we are already in non-conserved regions. So we should search for a letter. That's it. When you are here inside the non-conserved region, we are searching for letters. If there is a letter, like in the second string, then we consider it as insert states. But when we have gap, we move on to the next one and next one until we find the letter. This letter is actually inside the conserved region. So how many cases? We should count all the possibilities. 1, 2, 3. In 3 cases, I had no problem, and I could move on to the next region. So 1 plus 3, 4. So that's how I calculate the relative frequency. 2 over the total possibilities, which is 2 over 6, 1 over 3. 1 over 3, it is approximately 33%. And what about the other part, which we go with no problem from 1 inserted state to the conserved region? This is 4 over 6. So how did I calculate 2 and 4? You saw it wasn't easy, but if you see it once, then for the next ones, for the next profiles, you will have practice and it will be easy for you. So 67% we have the case that from the insert state, I move on to the conserved region. So as you can see, this one is practice. And for 33% of cases, there is a loop. I go back to the inserted letter. And as soon as I reach P4, the rest is pretty easy, because as you can see, when I reach the 7th position, for reaching 8th and 9th position with no problem, I go to the conserved region. So for 100% of cases, I specified with probability of 1 or 100%. If you don't write anything on the edge, it means exactly the same. It means that there's no other options. There's no deleted state. There's no other inserted state. Directly, I go to the conserved region to the match states. And finally, I reach the end. So as you can see, this is the way to construct a profile HMM. It takes time to get used to it, and that's why in the next weekly assignment we will practice it. And I won't wait for your submission in order to talk about it again, because we need practice for sure to master designing profile HMM. But for the time being, please make sure that you understood this example. Watch this video again and again, and let's try to do it even once without watching the video. Let's see if you can design the same HMM or not. And you may say, is it unique to design such a HMM? I mean, if you design one, should it be exactly the same as the one that I showed you or not? Well, this is not always unique. That's why we need to give you some limitations to have some standard in order to have our profile HMM. If you design a profile HMM which is different with this one, maybe this is true, but there is a high chance that you may have some mistakes in it. And that's why, in order to minimize our errors, in order to design such a profile HMM, we need to have some limitations. So these are the limitations that we want to strictly follow. We should be careful about obeying the probability distribution rules here. This one is very important because by mistake, if you design a profile HMM that doesn't follow the probability distribution rules, then this is not a profile HMM anymore. So we should be careful about it. We can't connect an insert state to another one. Only a self loop is allowed. So we should be careful about it too. It's not like we have I1, then from I1 we have an arrow to I2. In the previous example, you saw that this is not possible. So instead of that, we just show it like I1, and we will have a self loop, and it has a probability. So we don't need to define more I, for example, inserted states. We can connect a delete state to another one. So it's okay to do that. It means that it's possible to have D1 and connect it to another one. When does it happen? For example, here, assume that in the fifth string, inside the third position, instead of C, I had a gap. Then in that scenario, I could show it with D2. So this is possible, but I don't have self loop like the one for insert states. So self loop is allowed for insert states, but not for delete states. And vice versa, we cannot connect I1 to I2. This is not allowed, but it's possible to connect D1 to D2, for example. Number of match states should be decided and remain fixed. As you notice, based on the threshold, we decided that we have 6 number of match states, and it should be fixed throughout the design of the HMM. And also, we should be careful that order matters in the profile HMM. It means that you cannot connect P6 to P4, for example, have an arrow like this. Everything goes smoothly from P1 to P6 in order. P1 to P2, P2 to P3, and so on, okay? So we cannot go back from P6 to P4, which was kind of obvious. So there are other algorithms to deal with that for sure. I already mentioned about 2 classical ones, one of them related to dynamic programming. Profile HMM, the one that I showed you, somehow follows the dynamic programming as well. But if you are interested, you can go through the book and learn about those ones as well. But our focus mainly today was related to HMM, which is very important to know about it. This is very common to use that one. The user-friendly part of it would be also interesting for molecular biologists, because molecular biologists don't want to see, for example, mathematical equations. If you show them just the HMM, then of course they would understand it much better. So in order to communicate with other scientists in the field of bioinformatics, it's very important to have such models that everyone can appreciate it, and also it should be as powerful as a mathematical model anyway. One of them, which is pretty new comparing to other models, is PetriNet. PetriNet itself is used for 4 decades so far, but for using it for biological system is pretty new. And this one is very important because, as I said, it's user-friendly also in order to deal with that. We use graphs in order to show the model. It's very similar to HMM in that terms, because as you can see, for HMM we have we have places, we have transitions. For PetriNets we have almost the same situation. We have places like this, and we show transitions with line or a box, and we have arrows between them, arcs, and we can show weight as probabilities. So we have similar case in PetriNet as well. If you are interested, also you can read my articles related to using PetriNets for biological or psychological systems. I think about half of my published articles I used PetriNets. I mean, so far, if I'm not mistaken, I have about 80 or 19 publications, and about half of them I use PetriNets. That's why such models are very important, and HMM is one of them. But why do I prefer PetriNets comparing to HMM? Because it's very flexible, and I don't obey the rules that you observed that way. I have flexibility in designing my model, but of course it needs practice, it needs experience in order to not to create a wrong model, because you want to make sure that your model makes sense. If you design a model which is not related to nature, this is something just artificial, and you just made something which doesn't exist. That's why you should be careful about designing your model. So finding your own algorithm is very challenging. But as I mentioned, there are so many algorithms, and I just wanted to mention HMM for you because it was in the syllabus of the course. PetriNet is not. That's why I'm not going to mention it for the time being, but if you are interested, you can go through these articles for sure to understand in modern techniques how we can deal with algorithms related to biological systems. And for sure, we can use it for multiple sequence alignment as well. When we will talk about pathways, maybe I will have time to talk about PetriNets more, because it's very interesting to know about modern techniques as well. Okay, guys, if you have any questions, please let me know. Otherwise, I want to talk about your midterm a little bit.